2 of the Chapter 21 notes and demonstrations. Alrighty then. What we're going to do is go through this, which is a sample question, and then we'll go through a couple of sample problems here. And hopefully those will help you as you work through these in the next week or two on your own. All right, so here's a picture. Cut it out of your book, obviously, and paste it in here. And it shows these lines, which are known as isolines or equipotential lines. The AP is probably going to call these isolines. Iso meaning the same. So everywhere along these lines, we've got the exact same potential. So this one is 0 volts. This line is 100 volts. So probably everywhere on this line, including point B, would be 50 volts. And then if you go over here, so this goes 150, 0. This would now be negative 50, negative 100, negative 150, negative 200, negative 250, and then you can see negative 300. So we're getting very negative in terms of our voltage down here. So to find the electric, questions 22 through 25 are asking questions about this diagram. So what's the potential at point C? Well, I know that each of these equipotential isolines is changing by 50 volts, and I know that more negatives are this way. So this line is negative 300, negative 350, negative 400. So I would anticipate that being negative 400 volts. At which point is the electric field strength the greatest? Well, if you recall, electric field strength can be thought of force over charge or voltage over change in position. So I'm going to shrink that down. So in this particular case, I don't know why I'm moving this weird places. This case then, when you're thinking about electric field strength being the strongest, we're looking where these lines are closest together. Why? Because each line is a change of 50 volts, so if they're closer together, you'd have a stronger electric field. Interestingly enough, lines of electric force or electric field are always perpendicular to these isolines. So in this case, between A, B, C, and D, here they're very far apart, here they're pretty far apart, here they're very close. I don't even see a point D, so it's got to be point C where the field is the strongest. So in some ways, these are acting like what are called contour lines in earth science maps. So when you have a big change in elevation close to each other, they look really steep and the lines are close together. Here, this would be an area where, if this were a contour map, the elevation is changing slowly and over a big distance. So you would have a hill or mountain that would be less steep. 24, to estimate the field strength, we know that electric field is this. So if it looks like it's about 500 volts over 0.5 meter, so that change, and let me check here for a second because I want to check in the chapter to make sure I'm thinking about it right. Nope, videoing, yep. All right, so this is asking again the approximate magnitude of the electric field at point C. So when I look at this is kind of hard to think about, but if I look here, I'm going through, this is about 0.5 meters. I think I'm going through 1, 2, 3, 4, 5, 6, 9, 10. It seems like it's about 10 lines, and which is 500 volts and about 0.5 meters, so it looks like about 1,000 volts per meter, maybe a little less. The text said 800 volts per meter, which makes sense because it's getting a little weaker up here, and then very weak electric field here. So at point B, the question 25 is asking, is the direction of the electric field closest to up, down, left, or right. So in this particular case, at point B, this is an area of higher potential. That's an area of lower potential. So essentially what we've got an arrow, and the electric field is going to be a point perpendicular to the direction of the line changing. And I think it's actually going to be mostly vertical. So I'm going to say it's going to be down. Yep, mostly down. Okay. For problems, and these are in the back of your book also. So problem number 11 is saying an electron initially has a speed of 500,000 meters per second and is brought to rest by an electric field. So essentially, because an electron is negatively charged, this thing is going to be shooting to a region of lower potential. So to slow down a negative charge, you're going to need to move to a region of lower potential because we think of that as being more negative. Part B is saying, what's the potential difference that stopped the electron? Well, we're going to go think about energy with this. So I always like to start off with something like this. My initial energy is equal to my final energy. It's just in a different form. Now, that's not true if the energy is leaving the system, but here it would not be leaving the system because there's not any push on it from an external force. We're thinking of everything inside the system. So initially the electron has kinetic energy, and at the end it's going to have the same amount of electric potential energy. So the kinetic energy, 1/2 mv squared, that's the mass of the electron, that's the speed that was given. At the end, we know that the charge on an electron is negative 1.6 times 10 to the negative 19 coulombs, and the delta V, or change in voltage, is what we're trying to figure out. So this says, and again, this is the major formula right here we want to focus on. Sorry. This one right there. Well, you know the kinetic energy, and that's how you find the electric energy. So this comes out to be negative 0.71 volts. And if you want to convert that to electron volts, lo and behold, since we're talking about one electron moving, that's the number of joules we have, which is up here. That's the conversion between electron volts and joules, and so we get 0.71 electron volts. Notice those are the same. So if we think about the energy where it's ending up as being zero kinetic energy and all potential energy, we've gained this potential energy, even though we're dropping through a negative electric potential. So number 49, I think, deals with a capacitor. So it says a science fair radio uses a homemade capacitor of two 35 times 35 centimeter sheets of aluminum foil separated by a 0.25 millimeter thick sheet of paper. What's the capacitance? So and this is for part A. When I look at this, this is one of the capacitor formulas. I know that's the dielectric constant, that's vacuum permittivity, that's the area on a plate, that's the distance between two plates. So I've got to convert all this stuff in the standard unit. So 0.35 times 0.35 meters gives me that as my area. That goes up here. This vacuum permittivity is 8.85 times 10 to the negative 12th. So when I look at the table in my book, and I would have to go and take a look and see what page that's on, but I'm going to have dielectric constants, and these are on table 21.3 on page 760, and paper is 3.0. So that means for the same potential difference, the same voltage, something with a paper dielectric could hold 3 times the amount of charge at that same voltage as something that's just a vacuum. and then this is the distance in between them. That's 0.25 millimeter. So I get that the capacitance we're looking at is about 1.3 times 10 to the negative 8th farads, or 13 nanofarads. So the farad is a huge unit of capacitance. We will be using labs in class with capacitors that have 1 farad of capacitance, so they're very big. The second part of this says how much charge would be held on each plate if the capacitor is fully charged with a 6-volt battery. So now we go back to the capacitor formula we've seen before. So charge over voltage, rearrange charge is equal to capacitance times voltage. Well, we figured out the capacitance up here, and the 6-volt battery is here. So that tells us how many coulombs of charge could be held on each plate if this capacitor was fully charged. So those are just a couple examples of what's going on. And thanks for playing.